Okay, moving ahead, now we have a new chapter on alkenes. That is a very important chapter, and we'll be starting by introducing some important concepts on alkenes. Alkenes are very fundamental because they can be transformed into alcohols, into diols, into aldehydes, ketones. They are very versatile into interconversion into various reactions, through various reactions. So it's a very involving chapter and very important, especially because we have a lot of reactions under this chapter. So before we go into in depth into the alkenes, I want to introduce very important concept what the bonding in the alkenes is. First of all, they are made of sp2 hybridized carbon. This is a pi bond that is existing in the alkenes. If we take a simplest alkene, which is ethene, that is C2H4 formula with 1 degree of unsaturation, obviously. The bonding between these two carbons is 1 pi bond and 1 sigma bond, which makes a double bond. So the double bond in alkenes is made of 1 sigma and 1 pi. Overall, you have 6 sigma bonds. This is sigma bond, carbon, hydrogen, carbon, 4 sigmas in this, what you see. And also the 5th sigma is one of this, and 1 pi. And the molecule in alkenes, at least where the alkene double bond is flat. That means all of the hydrogens, these hydrogens, are on the same plane on the board, or if you flatten them like this, they will be flat. So it has 120 degrees between these two hydrogens, hydrogen, carbon, hydrogen, that's 120 degrees. And the pi bond is formed from an overlap of unhybridized p orbitals. That means the vertical unhybridized p orbitals with 1 electron on each one would make the pi bond. So it's really very important for you to understand the hybridization of an alkene, which is sp2 character, because it's unlike the ethane in this, which is a sigma bond, which is an alkane, fully saturated one. So the bond length also is different. For example, between CH3 carbon-carbon bond length in sp3 hybridized alkanes, it is 154 picometer. But when it becomes the alkenes, the carbon-carbon bond is shorter and much more stronger. So it is 134 picometer and 635 kilojoules per mole to break that bond. Because obviously, it is not one single bond. It is a combination of a sigma and a pi bond. So that double bond needs a lot of energy to break. While the sigma-sigma bond, carbon-carbon single bond for alkanes is 368 kilojoules per mole. Obviously, the triple bond is very, very short. The hydrogens on this are very acidic, and this hybridization is sp hybridized. This is sp2, like I just mentioned here. These are sp3. So these are some important understanding to have when we this new functional group. So now alkene is a functional group because you can have many compounds that have double bonds in them. But that double bond is not different from any other double bond. A double bond can be terminal, meaning that at the outside of the molecule, so this is at terminal, these are two hydrogens at the end. This is called a terminal alkene. Remember, a terminal alkene. This is internal alkene because the alkene is the double bond is between the chain, inside the chain. So in the internal alkene, you should also remember this is a transformers of stereoisomer, but can have also a cis for the same thing. For example, this is cis. This is trans. Still they are intermediates. Trans-isomerism is also one of the properties of alkenes. Remember, cis and trans. E or Z is a property of alkene. Terminal alkenes, they don't have cis and trans because these two hydrogens from on top of the double bond and down the double bond are the same group. You cannot differentiate between the two, so there is no cis-trans isomerism for a terminal alkene. While internal alkene, this large group and this large group are opposite side. The hydrogens are opposite side, that is trans. Here you have hydrogens and hydrogens on the same phase, that is cis. So for alkenes, from now on, what you need to remember is there is cis and trans isomerism. Alkenes are also very important because they are ubiquitous in biological systems. All the fatty acids, at least some of them, the unsaturated fatty acids, unsaturated fatty acid, they contain a double bond. For example, this doesn't exist here. Oh, this is, yeah, that's steric acid, not steric acid. That's not steric acid. The steric acid would be the one which doesn't have a double bond. So it's 18 chain. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it is a C18. It's called steric acid. Steric acid is fully saturated. It doesn't have any double bond. So the melting point for steric acid is 69 degrees. It's like butter. So the physical and the chemical property is widely also depends on how many double bonds you have. For example, here, this is called oleic acid. Oleic acid. This is linoleic acid, so that's not oleic. So the melting point drops like that at 4 degrees for the same number of carbons. So that is also a cis double bond, natural. For example, if you remember in food labeling, trans fatty acid is when this is trans, those are not good, but this is a cis fatty acid. Its melting point is 4 degrees Celsius. So the next one is linoleic acid. Linoleic acid, linoleic acid, which has 2 double bonds. The melting point goes down to -5 degrees. As you see, they become more oily and oily. So the saturated fat is, this is saturated fat, saturated fatty acid. So it's double bonds in the alkenes have significant application in biological systems. That's where they exist, making cell membranes and so on. So there are also some with 3 double bonds. All of them are cis. This is cis double bond. This is a cis as well. This is cis, not unsaturated trans fat. This is cis. This is cis. It goes to -11 degrees Celsius. So what I'm just trying to show here is how important they are, and we'll see the different reactions they undergo to become saturated, to add stuff. And for example, you can add hydrogen to it. For example, this oleic acid can be transferred to steric acid if you add hydrogen, right? So adding 1 mole of hydrogen across this double bond, that's what is called hydrogenated fat in the food labeling. That's what happens. When you hydrogenate this, it becomes saturated fat, which becomes like butter. So it would have that property by just from this double bond into saturated by addition of a hydrogen gas. So for hybridization, I have already posted in lecture 31. This is lecture 32. In lecture 31, I have exclusively discussed the hybridization of alkenes and the sp2 carbons. So please refer to lecture 31 just to see the hybridization. So from this on, we'll also continue to see some of the properties of alkenes. So alkenes have also stereoisomerism. Obviously, we have seen cis and trans, and this is a cis form. So there is a difference in terms of their general stability of these compounds or these stereoisomers. Here you see the trans one, and here is the cis. So the cis, where the two hydrogens are in the same phase, here the hydrogens are here and there, so that's the trans. So in general, the trans isomer for alkenes is more stable. So this is more stable. That is the cis form. So that's what we need to understand in general, the natural or the energy, the stability, because of this steric clash between two large groups. When the two large groups are on the same side, there will be a steric interaction between these two. That makes the compound to be more unstable, especially when you have large groups like that. So the trans is more stable because these two large groups are as far apart as possible. When it comes to cyclic systems, cycloalkenes, for example, cis cycloalkenes are the most common ones, especially if it is 8 carbon and less. Here we have 6 carbon, therefore it should be always, it should adopt a cis form. There is no way that this two bonds would be twisted and make a trans for smaller cyclohexene groups or cycloalkenes. So this is because of a restricted rotation. The restricted rotation makes the cis the most dominant structures. So when you have number of carbons less than 8, the ring system would always adopt cis, a cis form. So that's one thing we need to know when we consider alkenes. Moving on, one general idea about alkenes is the degree of unsaturation. We call it the degree of unsaturation because if you just saturate this with a hydrogen, 2 hydrogens, it will get too saturated. So the saturated system and the unsaturated system, this is alkene, this is alkane. So this is 1, 2, 3, 4, 5, 6, hexane, and this is hexene. So this is unsaturated. So how many degrees of unsaturation this compound has? Just 1 degree of unsaturation. If you have another double bond, for example, if you just add one more in the cyclohexene like this, there is 2 degrees of unsaturation. 2 degrees of unsaturation. 2 unsaturated double bonds. That's the conjugated double bonds. So the formula for this would be C6H10. So in general, we can calculate the degree of unsaturated if we are given a formula something like this. For example, for C6H12, the degree of unsaturation is 1. That means the formula ring or double bond. So this formula tells you how many rings or double bonds you have. Unsaturation is because of one ring system, and it could be one double bond. So for example, here cyclohexene has 2 degrees of unsaturation because you have one double bond and one ring system. So it could be ring plus double bond, or totally like this one, it will be just the alkenes or the unsaturation or the double bond. Let's calculate for C6H12. C6H12, it has just 1 degree of unsaturation. 2 times 6 is 12. 12 plus 2 is 14. 14 minus the number of hydrogen, 12. 14 minus 12 is 2. 2 over 2 is 1. So the degree of unsaturation for this is 1. For example, for C6H10, which has 2 degrees of unsaturation, we can calculate C6, that is 2 times 6, 12. 12 plus 2 is 14. 14 minus 10 is 4. 4 over 2 is 2. So there is 2 degrees of unsaturation. Here 1 degree of unsaturation, one double bond. Let's see this. What's the formula first for this? If we're given a formula, we can come up the ring plus double bond. So as I already told you, the ring plus double bond, or the degree of unsaturation, is 1 plus the ring system is also counted as unsaturation. So I have 1 hydrogen, 2 hydrogen here, 2 here, 4, 6, 8, 10. C6, H10. What is the ring plus double bond in this? If I am given like this, it could be open chain like this with 2 degrees of unsaturation, or C610, H10, which are constitutional isomers. It could also give 2 degrees of unsaturation. So for this, the ring plus double bond calculation gives you 2. 2 because one of the ring system is counted as 1 degree of unsaturation, and the double bond as 1. So 1 plus 1, 2. So this is some general overview of alkene. We haven't gotten yet to the different reactions, kind of reactions alkenes undergo, and so on. So next, I will show a few points on the nomenclature of alkenes. So I'll continue. So like new functional group alkenes, they have also their nomenclature. So we have to be familiar with how we name alkenes and how to write the structure for if the name is given. So if you just look at here, this alkene, you have a 7 carbon alkene at 3 position. 1, 2, 3. The alkene gets a priority over the metal substituent. So at 3 position, I have the double bond. Therefore, it would be a 5 position, 5 metal. It is a 5 metal, 3 heptene compound. Heptene, ENE at the end. 5 metal, because at 5 position, this is 5 position. The double bond is at 3 position. That's why it's called 3 heptene. The longest chain is a 7 carbon chain. Let's see this one. So always you have to include the chain where the double bond is included fully. That means you cannot just count like this, but you have to count 1 here, 2, 3, 4, 5, 6, 7. This is as well a 7 carbon double bond alkene. So this is an internal alkene, just to mention, because the double bond is between carbons. Here this is a terminal alkene because you have hydrogens on this side. So this is a case where the ethyl is substituted at 2 position. So we can call this 2-ethyl. 2-ethyl. So it is a heptene. We don't have to say 1 heptene. This is a 1 is already known if the double bond is heptene. ENE, remember, we have an alkene. Here we have a cyclopentene system, a cyclopentene which has also a substituent. So the substituent is a metal group. So at 1 position, this is 1, this is 2. So at 1 position, I have the alkene, meaning the double bond, as well as the metal group. So this is just a metal, 1 metal, cyclopentene. Remember, ENE is for alkene. Let's go to this one. This is a cyclohexene ring, a 6-member ring, and it has 2 substituents as well, But the way you count, always be careful. This is carbon number 1, highly substituted double bond is a priority always in this case. But you don't count this way. Be careful. So the way we count this would be, if we are starting this terminal is the terminus of the alkene, we go over the double bond. 2, 3, 4, 5, 6. It makes the metal group to be at 6th position. So what I have is a 1,6 dimethyl, because I have 2 of them, a cyclohexene. I don't call 1 position because it's known that if I am not mentioning where the double bond is, that means it is at 1 position. This is how you would name when you have only the alkenes. But it's a little bit different when you have an alcohol and an alkene functional group together. Obviously, the functional group alcohol gets the first priority over the alkene. Remember this. Alcohol, OH, is more priority than a double bond. Okay? So let's count this. Obviously, the alcohol is at 1 position. That's where we count. And we'd include the longest chain where the double bond is on. So this is carbon number 1, number 2, number 3. At 3, you have a double bond. At 4, you have an ethyl group. So it is a 4-ethyl. 5, 6. So it is an hexene compound. Okay, so it's hex. So the naming here is a little not like straightforward heptene, hexene, and so on like that. We have a slightly different way of naming this. So this is a 1-ol position. Ol is for alcohol. So at 4th position, 1, 2, 3, at 4th position, 4-ethyl, okay? This is a hexenol compound, so we call hex. And now you mention where the double bond is at 3En, 3N, and 1-ol. So I will review again this. First you have to see the number of carbons. It would be hex, pent, hept, and so on. That's how you would name it. And the double bond gets a name En when you have more than 1 functional group for a double bond. So at 3rd position I have ethyl group, which is this one. This is 4. This is 1 position. But 3 is the first thing you encounter, that is 3. So now 4-ethyl, hex, because it is 6 carbon, 3 where it is En, that's En, the alkene, and 1 where the alcohol is, 1-ol. Okay, let's do the same thing here when we have an alcohol and an alkene group. So I have here a longest chain, 1, 2, 3, 4, 5, 6, 7. This is a hept system, hept. But the En is at, the ol is at 2 position, 2-ol. That is the last one you should always mention because it has the highest priority as well. So it should be mentioned as the last in the name because it's an alcohol compound, but it is an En and alcohol. So this is a hept, but the hept has also a double bond, 1, 2, 3, 4, 5. Remember, at 5 position I have metal as well, and at 5 position I have the double bond as well. So this is named as 5-methyl metal. It is a hept compound, 7, hept, I think it's hep, not hept maybe. it's hep, I think. Yeah, it's hep. 5 methyl hep, the double bond is at 5 in 2 ol. So that's how we name a 5 methyl. No, did I make a mistake? It should be a 6. 1, 2, 3, 4, 5, 6, 7. 6 position. 6 methyl, 6N, 2 ol. This is a 6 methyl hep 6 and 2 ol. So what does it tell me? At 6 position I have methyl group, and the double bond is at 6 position. It is a heptene, meaning a 7 carbon compound. At 2 position I have alcohol. Let me jump to this one because it has also alcohol and enol in. So let me just count this. For this compound right here, I have the longest chain, which contains the alcohol, and also the double bond is this one. So it's 1, 2, 3, 4, 5, 6, 7, 8. So this is an oct compound. At 1, 2, 3, 4, 4 position, it's 4 ol alcohol at 4 position. And at 1, 2, 3, 4, at 5 position, I have ethyl group. At 6 position, I have methyl group. So this is 5 ethyl, 6 methyl, an oct compound, because it is 8 carbon. Let me just make a little more space here. Oct. At what position is the double bond? 1, 2, 3, 4, 5, 6, 7. Oct 7 in, and the alcohol is at 4 ol. So let's just read out this. It's a little bit long. 5 ethyl, 6 methyl, oct, 7 in, 4 ol. So at 7 position I have a double bond. At 4 position I have alcohol. At 5 and 6 position I have ethyl, and 6 position methyl. So it needs a lot of practice and do a lot of exercises. You can get it easily. So here I have a cyclo system, which is much easier. So between this alkyl group and between this, the priority is for the double bond. So the double bond, if I say this is a 1 position, this is 2, this is 3. So it is at 1 position I have the alkene, and at 3 position methyl. So this is just can be named as 3 methyl, and I believe it is a 7 carbon system. So it is a cyclo and heptene. It's just one functional group, so you name it like this one, not like this one. So it is a 3 methyl cycloheptene. So this needs a bit of exercise, but there is also a stereoisomerism in the naming, which I will introduce here. The stereoisomerism in alkenes is a cis and trans. So for example, here you have a cis system. This is a cis because if you just compare across the double bond, the highest priority between this and this group is this one. The highest group between this and this one is this one as well, ethyl group. So both are facing on the top on one side. So this is a cis. When we name this, we call this cis. 1, 2, 3 position I have a double bond, 3. So this would be a cis 3-hexene. Cis 3-hexene. So in this case, this would be trans cis 3-hexene. hexene, cis and trans. So that's what just I introduced, because if you just look at this one, there is hydrogen there. Don't forget this. The largest group here is on this side. The largest group between these two is this one. So those are trans. So let's also see here what I have is a 1, 2, 3, 4, 5, 6 system. This is a hexene still, but at 1, 2, 3 position, 1, 2, 3 position, I have metal group. So this is a 3 metal. This is first, is it trans or cis? Let's determine this. This is hydrogen. The priority is up here. Between this metal group and this ethyl group, priority is down here. So this is a trans compound. So we call this trans 3 metal group, trans 3 metal, and this is a 2 pentene group. So if you just have this 1, 2, 3, 1, 2, 3, yeah, so at 2 position I should have 1, 2, 3, 1, 2, 3. Still it is the same. 1, 2, so it's 3 pentene as well. How is it named? 1, 2, 3, 4, 5, 6. So this is 3 pentene actually. 1, 2, 3, 4, 5, 6. So what should be pentene? It should be hexene. 3 hexene. So let me just double check here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3. 3 position I have metal group, and at 3 position I have the double bond. So this is correct. So here I have both are, this group is smallest group down there, metal group down there. This is the cis. So the cis has at 1, 2, 3 position I have metal, 3 metal, and at 1, 2, 3 position I have the alkene group, so this will be 3 hexene. So this is a 6 carbon, 1, 2, 3, 4, 5, 6. So this is how you name cis and trans. So this would give you overall how the nomenclature in alkenes are, and now we'll continue to other chemical and physical properties of alkene. Okay, let me say some few words on E and Z isomers as well. Those are similar to cis and trans. For example, in naming this compound, this is between chlorine and bromine. You have a priority for bromine, and you have metal and hydrogen. Here, this is metal group, and so this is obviously an E isomer of an alkene. So in naming this, we will introduce that it is a 1E, 1E. So it's a 1-chloro. Let me just make it alphabetical. So it's a 1-bromo, bromo, 1-chloro. It is a propene, so it's a propene, 1, 2, 3 carbon. So it's 1 propene, so it's chloropropene, an alkene. So the E shows that this is a trans isomer because a priority would be bromine here and a metal would be here. That's metal group. So that's why we have an E isomer. For this one, if you just look at here, this is a propyl group and a bromine group. A bromine and ethyl group, I think the bromine takes precedence and the metal would get precedence. So this is an E isomer as well. So the double bond is at 2 position, so it is a 2e position. So it's called 2e, and at 3 we have bromo, 3 bromo. So the rest is 1, 2, 3, 4, 5, 6. So it is a hexene. So at 2 position we have 2 hexene. So it is 2e. That means it is E isomer. At 3 we have bromo, 2 hexene. 1, 2, 3, 4, 5, 6. 6 carbon, which is hexene. And some also, just some detail here, double bond which are just attached to outside of any cyclic system, they are called methylene group. So because it's CH2 here, which is methylene. So it is a methylene, not methylene, but methylene cyclohexane. Methylene. So this is a methylene group. Methylene cyclohexane. So that's how methylene cyclohexane. So such group are also called vinyl group. Vinyl group is something a substituent with just a double bond, but if you have 1 carbon more as substituent, it's called allyl. Allyl, that is an allyl group. It is a 3 carbon substituent, 1, 2, 3. This is allyl, this is vinyl. So it's vinyl. So if this is called a 1-vinyl cyclohexene. Cyclohexene because there is a double bond, but as a substituent, a double bond as a substituent is called vinyl group. So this is allyl, this is 3 carbon. Vinyl is only 2 carbons. So those are the distinction you need to know when we discuss an alkene. In overall, the physical properties of alkenes is not very different from alkanes, where the only van der Waals forces are very weak. They are not very much. So, but there is a slight difference in van der Waals forces between, for example, a cis and trans. For example, this is cis and this is trans. So if you just look at the boiling point of this two, the boiling point is higher for this one. I'm sure this is higher boiling point for the cis. This is lower. So the way this is justified why the cis has higher boiling point as compared to the trans is because the cis has some kind of dipole moment towards this carbon and net dipole moment towards that carbon. As you know, sp2 carbon is more electronegative than sp3, so electrons are withdrawn towards this carbon. So there is a net dipole moment. So there is net dipole moment for this one. Let's see on this one. The dipole moment here is something like this, right? And for this one, it is something like that. So the dipole moment cancels out. So there is no net dipole moment, no dipole moment for interaction. So hence, it has a lower boiling point. This is some of slight details which you need to read in the book, and we'll continue discussion more on. Okay, now we are going to the main portion of alkenes, their reaction, how they are made, but most importantly, how their reaction is to be transformed to different chemical compounds. if you remember in chapter 9, we have covered dehydrohalogenation. That means we're eliminating an alkyl halide and one of the beta hydrogens to make an alkene compound. Or we were using alcohols for dehydration of alcohols to give us an alkene. So this is how alkenes are made, either dehydrohalogenation or dehydration of alcohols. That's how they are made, by an E2 mechanism. So E2 mechanism would give us an alkene compound. That was extensively discussed in previous chapter. That would be chapter 9. Now we are in chapter 10 on alkenes. And the main part of the chapter 10 would be how alkenes react with different reagents. So the main reaction is what they do is opposite to elimination reaction. These are elimination reactions where the alkenes are made actually. But in their own reaction with something else, alkenes react like this. It's called addition reaction. So, for example, this sodium etoxide is a strong base. By E2 type of elimination, you can make a cyclohexene compound by elimination. So these are all elimination. So here also you have an alcohol group which is tosylated to be a good living group. One of the beta hydrogens from here would be eliminated, and this one also moves out. So this is the alpha carbon. Here you have alpha carbon, beta. So this is the elimination reaction we have already covered. So I encourage you to just see how we have made alkenes in chapter 9. This is all the lectures up to lecture 31, 32 in my video series. You'll find them lecture 29, 30, 31, 32, all of them. Now we are in lecture 33, which is on alkenes, and you'd see how alkenes are made. But the purpose of this new chapter is how alkenes react with different reagents. For if you have XY reagent, it will be adding across that double bond. The pi bond would disappear and it gets saturated. It adds XY across the double bond. The X and Y would be added. That's why it is an addition reaction. As a result, the pi bond is disappear. Pi bond is used already, used up, and it gets saturated, meaning that there is no double bond anymore. So everything becomes from sp2, the carbons actually become sp3 hybridized. These are sp3 hybridized after addition of XY. So, but these were sp2, sp2. So, in general, what I would encourage you to just remember is now what we are doing would be opposite of what we have been doing, like making the alkenes, but now we are reacting alkenes to make several different chemical compounds. You will see how much alkene is very important in organic chemistry. They can be transformed to so many different chemical compounds. They could be alcohols, they could be alkyl halides, they could undergo oxidation to be aldehyde, ketones, different functional groups. So these are important reactions that we will learn in this chapter. So we'll continue on addition reaction of alkenes.